You might also hear me refer to this just as the rational functions unit, but really it's four because it's the fourth unit that we're doing this one. Okay? All right? But they're interchangeable. Okay? So over the course of the next 2 weeks, we're going to be deep diving into rational functions. Okay? We don't solve them. Okay? We graph them. So this is a graphing unit. Okay? So our goal in the next couple of days is to get the foundations to graphing rational functions. Okay? But first, let's start by figuring out what a rational function is. Okay? So in the last unit, we talked about rational numbers. We used the rational zeros theorem to figure out a list of all of the possible rational zeros that a function may have. Okay? Now, how did we do that? How do we figure out that list of numbers? So we took the factors of the last number and did what with the factors of the first number? Divided. Okay? Now you'll see this how I'm getting here. So we're going the long way around. Okay? So we divided numbers, right? And we called those rational zeros. Okay? Okay? So a rational number is a number that can be divided. With me on this? Follow my logic so far? Okay? What's another way of saying what a rational number is? A rational number is a number that can be divided. Saying one word. A rational number is. Okay. What does it mean to divide? It means what? Fraction, right? Fraction. Yeah. Rational numbers are fractions. Oh, long way around. Rational numbers are fractions. And they come in many different forms. We could have positive ones. Give me an example of a positive fraction. 1/2. Give me an example of a negative fraction. Negative 1/3. All of those are rational numbers. Okay? They could come in improper form. We like improper fractions, right? Better than mixed numbers. So what's an improper fraction? 4/3. Right? Here's my question to you. Is a whole number rational? Why? Put it over 1, right? Okay. Or any number, right? Like 16/2. Okay. 72/9. All those are still rational. They're still equal. Yeah. Okay. Like it. Same thing with negatives there. What about 2.5? What are you saying yet? Fraction? What? In fraction. Because I know what you want to say. You want to say 2.5/1. Because what's wrong with that? Just wait. 2.5/1 doesn't work because we can have a decimal fraction, right? Okay, now we'll go 5/2? Yeah. Mm-hmm. Oops, this should have been right. Just can't be 2.5/1. There's a lot of stuff here that you need. Trust me. Okay? So, if a rational number is a number that can be written as a fraction, what do you think a rational function is? Fraction with a variable after it? Okay. That's one guess. A rational number is a number that can be written as a fraction. What's a rational function? Bingo. Yeah. So a rational function is a function written as a fraction. So we're going to have funky looking fractions. Okay? Now, it may look nice and pretty, like f of x equals 1 over x. We're actually going to explore that one as our last example. It may look a little more complicated. It may look just flat out ugly. But all of those are rational functions. Now, there's an extra component here. Q of x is not the zero polynomial. What does that mean? First off, where in our function is Q of x? Nope. It's in the bottom. It's in the denominator, right? Okay. So what would the zero polynomial be? If Q of x is not zero. What's that mean? Q of x is not the zero polynomial. What polynomial is equal to 0? Okay. You're right. Yeah. There's only one polynomial that's equal to 0. Zero. 0 is the only polynomial that's equal to 0. So the 0 polynomial means that Q of x cannot be 0. Why can't Q of x be 0? Because you can't divide by 0. Because Q of x is downstairs in the bottom of our fraction, the denominator of our fraction. So Q of x can't be 0. That's the only restriction that we have in rational functions, is that the denominator has to be a number other than 0. Okay? Or it has to be something other than 0. That's our only restriction. Now, the first thing that we got to do with all of these problems, and again, we're going to be building the framework here for getting you to do so that when in 2 weeks we're all doing the exact same thing. First, second, third, fourth, fifth, bam, there's our graph. That's how we're breaking it down. So the first thing that we have to do is we have to figure out what the domain of our function is. Okay? Now remember that the domain is our inputs. It's what we put into the function. So our domain is going to be all numbers except the ones that make the denominator be 0. Okay? And so what's going to happen here is you're going to write out what the domain is, and every single person's is going to look like this. Okay? It's going to start with a capital D. Capital D stands for domain. So this is saying the capital D is telling you in your brain that the domain of my function is. Okay? Then the next part is saying all real numbers. That's that funky symbol for all real numbers. It's an R with a double vertical on it. Okay? And then in here is going to go your exceptions. Okay? So what this says then is the domain of f of x is all real numbers, but it's got a big old but. Okay? So the domain of my function is all real numbers except or but these numbers. And then you're going to fill those numbers in. Okay? Let's talk about where the denominator is 0. So in order to do that, let's use this function. So f of x is equal to 7 over x minus 2. The very first thing that we have to do is we have to find those exceptions. Okay? And so what we're going to do is we're going to set our denominator equal to 0 and solve. Because our denominator can't be 0, we're going to set it to 0 to find out those spots where it is 0. Okay? So in this case, that would be x minus 2 equals 0. Quick solve gets me x equals 2. So if I plug 2 into my function, I should get a denominator that's equal to 0. Right? 7 on top, 2 minus 2 on the bottom, 2 minus 2 is 0. So I get 7 over 0. You guys just told me that we can't divide by 0. Okay? So this right here, this is my exception. So my domain here would be all real numbers except x cannot be 2. So what happens at 2? Okay? Because we're going to have this graph, and we're going to be flowing on this graph, and then all of a sudden we're going to get to 2. And now we don't know what's going on. Okay? So what happens there is actually something called a vertical asymptote. Now, vertical asymptotes are very special. You've dealt with them. Again, you had in Algebra 2, you had a unit on these rational functions. Okay? So a vertical asymptote is a line off the start, right off the start. All of your asymptotes are lines, okay? Which means they need to have line equations or linear equations. Okay? That my function your function can never, ever cross. It is the wall of all walls. It's like saying Chuck Norris is right there, and the function's getting closer and closer to it, and it's got to, nope, can't cross Chuck Norris, I got to turn away. Okay? So your vertical asymptote never, ever, ever gets crossed. When we get to put it on the graph, it will go on our graph as a dashed line. And it will have to go on your graph. Okay? It's got to go on your graph. We find what they are from our exceptions. Or our restrictions in the domain. So in this particular case that we just had, x equals 2 was an exception. So x equals 2 is our vertical asymptote. Okay? It's the exceptions, the restrictions in your domain. Okay? The form of your vertical asymptote is x equals some number. If you just put the number, you're wrong, because a number is a number. X equals a number is a vertical line on my graph. So just putting a number, because there are going to be problems later on where I say, what are the vertical asymptotes? And if you just say 2, you're just giving me a number.
Sure. Translate into which language?
Yeah, exactly. Easy there, Siri. Okay? Siri wanted to translate that. Okay? Now, the kicker is there can be more than one. We'll have graphs later on this week that have more than one vertical. Okay? Now, what I need you to do now is I need you to find in your notebook somewhere a completely blank piece of paper. Nothing on the front, nothing on the back. Okay? Then I need you to rip it out of your notebook. You will have to determine if you are a fringy type person or if you're not a fringy type person. Okay? But what I need you to do is up at the top somewhere, I need you to put your name. Very important that you put your name somewhere at the top of your page. Okay? Okay? The reason that that's important is then this way, if you lose it, we can get it back to you. Okay? Because this sheet, we're actually going to start studying for our final right now. Okay? What we're going to do is we're going to fill up the front side of this sheet with the 8 steps to graphing a rational function. Okay? And then that way you can have an easy cheat sheet to, oh, look, this is what I do first, this is what I do next, this is what I do next, and so on and so forth.
So we can use this on the Bible.
Yep.
Amazing.
Yeah.
It's probably
Okay? So, at the top of your top of your sheet, somewhere, up there, you want to put down the steps to graphing a rational function. Now, what you're going to do, though, is you're going to skip some space for step 0. I know it sounds crazy, but we're going to actually have a step 0, and it doesn't come until like a week and a half later. Okay? But we'll get it. So I skipped some space for a step 0. I was telling kids earlier they skipped like 2 lines, okay, for step 0. Then we're going to have step number 1. Steps to graphing a rational function. Oh, need this part? That part's if you want. Yeah. I mean, it'll help. It'll help because we need the A and the B, but it's just basically you'll have all of this all the way through. Yep. So step number 1 says we need to find the domain and any vertical asymptotes. How do we do that again? Set what equal to 0? Set the denominator, the bottom equal to 0. And then solve, right? Okay? So that's what we need to do. Set our denominator equal to 0, and then we solve. Ready? Let's do it. now we're back in our notes. Keep your sheet off to the side or right in front of you, or you're going to want to have your sheet out whenever you're doing homework, whenever you're in class, etc. You want that sheet out for the rest of this unit for sure. Okay? So f of x is equal to 1 over 2x minus 5. Okay? We need to find the domain and the vertical asymptotes for this. What do I do? What's my denominator? 2x minus 5. So I said 2x minus 5. I set that equal to 0. Add 5 to both sides. Two x equals 5. Divide both sides by 2. X equals 5 halves. Yes? Okay. So, the domain of this function is what? All real numbers, but which means, what is my vertical asymptote? That's a number. X equals 5 over 2. And we're going to shorten up vertical asymptotes to VA. We'll have VA. Tomorrow we'll have HA. Later on we'll have SA. And we have all. Horizontal is HA. Slant is SA. Okay. Now, let's talk logic here. Okay? We have to talk a little fractional logic here. So we're going to make you think today, tomorrow, and Wednesday. Okay? If I take some number and I divide that by a bigger number. With me? So if I take something like 4 and I divide it by 1,000,000. Is that number going to be big? Small? What? Really small, right? Right? Okay. Because the bottom is bigger than the top. Right? Now, let's say I make that bottom number be even bigger. What's going to happen to my number? It's going to get smaller, right? Okay. So if I said that, so like if I send that denominator to infinity, right? That number is going to keep getting smaller and smaller and smaller and smaller and smaller as I get closer and closer to infinity, right? So what's that number really approaching? Going to 0. Right? Yeah, it's going to 0. Okay. Will it ever get to 0? No, but it's going to get so close that you can't tell the difference. Okay? Now, let's flip that around. What if I got a number and I divide it by a much smaller number? So for instance, 4 divided by 1,000,000. Fractional logic tells me when I'm dividing fractions, what do? Keep, change, flip, right? So this would really be like 4 times 1,000,000 over 1, which is 4 times 1,000,000? 4,000,000. Get it? Huh? So that number is going to get bigger and bigger and bigger, right? That's going to be a big number. So if I take 4 and I divide it by a number that's keep getting closer and closer and closer to 0, what's going to happen to my number? Tim, wake up. What's going to happen to my number? This number right here. The smaller my denominator gets, what happens to that number? What? It gets bigger and bigger and bigger, so that it goes to infinity. So if you divide by a big number, you're going to 0. If you divide by a small number, you're going to infinity. Okay? Just remember that. Because now, what we're going to do is we're going to do 4 problems all in one. Okay? The first thing is we're going to find the domain. Because that's the first thing we had to do in all of our problems. The second thing is we're going to find the vertical asymptote. We found the domain, we might as well find the vertical asymptote. The third thing is now we're going to use logic to describe asymptote behavior. Asymptote behavior is new. It's what your function is doing on either side of your asymptote. So as that function's getting closer and closer and closer to Chuck Norris, is it turning to go to infinity or is it turning to go to negative infinity? Because it can't cross. We learned that right away. It can't cross over. It's got to make a turn and go one of those ways. And then the fourth thing that we're going to do is we're going to find end behavior. We've done that. That's what the function is doing at positive infinity and negative. Okay. So let's start. First off, domain. What's the domain of this function? All real numbers except for 0. Do we agree? Okay. So domain is all real numbers except x cannot equal 0. Okay? Which means what? What's my vertical asymptote? X equals 0. So this was number 1, this was number 2, this was number 1, this was number 2. And we said x equals 0 as our first thing. Okay? Love it. Okay? Now we got to use logic. Let's scroll down. Asymptote behavior. Oh, yeah. So I've got this asymptote right there at x equals 0. Agree? So as I come in to this side, My function's getting closer and closer and closer from the left. Right? Okay. So 0, that means I'm getting smaller and smaller. Oops, that's bad. That's a bad small. Oh, no. Right? We're getting a smaller and smaller negative number. So if I put that into my function, 1 over a small negative number, divide by a small number, it's going to get big, right? Divide by a small number, gets big. Okay? What if I divide by a positive divided by a negative small number? What's that going to go to? Negative infinity. Yep. So my first one. Now here's where this changes a little bit. So how we would say this is, as x approaches 0, right? Because now x is approaching 0, but I'm approaching from which side? I'm approaching from the left side. So here's how I indicate that I'm approaching from the left side. Because left is the negative side on a number line. So I'm going, as x approaches 0 from the left, you just said my function is going to negative infinity. Let's try it again. This time let's approach from the right. Now I've got a really small positive number that's getting smaller and smaller and smaller. Right? So I'm going to have 1 divided by a positive small number. Which way is it going? Is it going to go to positive infinity or is it going to go to negative infinity? Positive, because it's positive divided by positive. Right? So how we would write that would be, as x approaches 0, but now I'm approaching from the right. Agree? The last thing we have is our end behavior. So way over here now, x is going off to infinity. So I have 1 over a huge positive number. What's that going to go to? My denominator is going to keep getting bigger, bigger, bigger. It's going to go to 0. Is it going to be positive or is it going to be negative? Positive, because I got 1, which is positive, divided by my huge number, which is positive. So because there is still something there. We talked about that, right? But it's not quite. We're getting closer and closer. So we say this as x goes to infinity, f of x is going to 0, this time from above. So we put a little plus sign up there. That's saying that it's going to 0 all above. one last one. X is now going to negative infinity. So I've got positive 1 over a negative huge number. Right? So that's going to go to what? Denominator is going to keep getting bigger, bigger, bigger. So that's going to go to 0. But from above or from below? Below, because now I got a positive divided by a negative, right? So that one's going to be as x approaches negative infinity, f of x is approaching 0 from below. Again, there's a video for you to watch tomorrow. It's 15 minutes and 51 seconds long. I checked before class. Okay? It has I think it was three examples of that logic. So what my recommendation for you is, start the video, pause the video when you see the function, do what it's asking, then unpause the video, and go through my explanation. Okay? On all three examples. Okay? On to this week's homework, on the yellow homework sheet, you can do number 1 right now. Okay? So you can do number 1 today. Watch the video for extra problems by Wednesday. I'll grade that Wednesday first thing when we get to class.